Lecture 35, and we continue our discussion on stabilizing effects of filters. We can pick up any unstable method, and we can actually design a filter in such a way that we have a stable method. The property of the filters is defined in terms of what we call as a transfer function, which is the quotient of the Fourier Laplace amplitude after and before filtering, and this kind of implicit filter that we are applying here in an explicit manner alters the numerical amplification factor G by a convolution with the transfer function to give us altered numerical amplification factor upon filtering, and we try to figure out what are the operational parameters in the physical plane itself. And as an example, we show how second order filters, central filters are designed. This requires satisfaction of a consistency condition and prescribing a transfer function at a particular value of k h, which happens to be at the Nyquist limit of k h equal to pi. Subsequently, we discuss the properties of the various ordered central filters, and we do it by adopting once again a global analysis. And we noticed that if we are to be solving a non-periodic problem, we need to adopt once again near boundary filters, revert back to a higher order filter in the interior, and as we go near the boundary, we can keep on reducing the order of the scheme, and this is what is called as the least ordered central filters or LOC scheme. This is also again given by the Gaitonde and his colleagues. We show how this can be effectively used. We also talk about the various filters that one uses near the boundary. This one sided filters actually leads to a complex transfer function, and this can lead to alteration of dissipation and dispersion properties. This is what we discuss in detail, that filter parameters are important. But we also note that we can play around with the frequency of filter. That means, how often we perform the filtering can determine the quality of the solution. But what is more important, that at times we notice that in a multidimensional problem, the filters applied in different direction works differently, and this directionality of filters in association with the physical nature of the problem can be a major source of error, and this is what we discuss on this finally. So, let us start on our discussion again on filters. I suppose you have also seen the assignment now. Now, you know what filters can do. Your assignment tells you that if you have an unstable method, you could use a filter carefully and make it stable, right. So, that is precisely what we are trying to do. So, suppose the basic principle remains the same, that if you have an evolution equation of this kind, okay. So, what you are trying to do is you have some solution, let us say depends on space and some time, let us say T n, and through this equation you actually arrive at like this. Okay. So, we actually march in time via some algorithm, and using this equation we arrive at the new time state. It may so happen that this process of direct application of the method on the differential equation may lead to numerical instability, like your assignment. I have purposely suggested that you take a method which is inherently unstable. We know that. We usually would see that if we go to the corresponding k plane. So, this is your physical plane. In the k plane, what we would be looking at is the u function for a wave number k, and this would take you to the next time step. And what we defined this method was in terms of the G, the amplification factor, which we called it as a function of k, as the quotient of u of k evaluated at the advanced time level divided by the predecessor. So, this is the definition, and your assignment tells you that we have purposely chosen a method which is greater than 1, right. So, this is your condition for numerical instability. So, for that k component, you are noticing that the method is unstable, right. If the method is unstable for any k, then of course, the overall method would not be workable. But then what we are saying that we would like to use a filter, and for the filter we will define what we defined the day before was a transfer function, right. We did talk about a transfer function here via use of some filters, which is given there. So, this transfer function, what is this transfer function? This transfer function we would define we'll take whatever we have obtained via the time integration. So, this is your time integration step. Via the time integration step, you have arrived at u of k plus k at t n plus 1, and the filter takes that solution and operates on that given by this. So, I will call this as okay. So, basically we are using an auxiliary function which we call it the transfer function, and we have noted how that comes about as this implicit equation. Please note that this equation is implicit, and this is exactly like your tridiagonal system that you would like to use because of its ease of operation, but we will call this filter as explicit. Why? Because we are getting the solution here, and then we are explicitly applying a filter characterized by this transfer function. So, we are basically going to multiply the obtained numerical solution at the advanced time level with this transfer function to get a solution, filtered solution, which is little more well behaved. That is the whole idea. More well behaved in the sense, right now to begin with it is greater than 1, we would like to bring it to exactly equal to 1. That is essentially is your assignment. So, you have to take an unstable method, you have to choose this transfer function very carefully, so that you get a perfectly neutrally stable algorithm. Okay. So, that is probably the best way of understanding what filters can do for you. So, basically what happens here is that this is the accepted solution, right. This is the raw solution upon the application of the numerical method. You take the raw solution, convolve it with the transfer function to get a solution which will be acceptable. That is your numerator, right. So, basically then we can define g hat. G hat is essentially the composite gain function, okay, amplification factor. So, this is a combination of then we'll write it like this, that g hat will write it like this, that this will be the accepted solution at the advanced time level divided by the solution that you had started off before the integration, right. So, what you can see that this we can simply write it as u hat k of t n plus 1 divided by u at k t n plus 1 times now. Of course, you can see this quantity here that we have written here is here the transfer function, right. So, that is what you are doing times this. What is this? This is our original amplification factor, right. So, now you know what is to be done, very easy, that you have a g of k which is greater than 1 and you will multiply with the TF, so that this remains well behaved, right. For your problem, what has been given? You have been given a packet. So, the packet is fixed at a single wave number, centered around a single wave number, right. That is what you have seen, that kh basically defines the central wave number. So, all you need to do is find out for that value of kh, what is this quantity. You design this so that you get this g of hat g or k equal to exactly 1, right. I thought I will explain to you what is in a sense you are expected to do in your assignment. And now the main question that remains is, how do you design the transfer function, right. How do we do that? And that is what we discussed in the last class, that we obtain the numerical solution, those are there on the left right hand side, and then you apply a filter of this kind. Okay. Essential idea remains that you end up solving a linear algebraic equation of this form, with A being again a simple tridiagonal scalar matrix, and that is that. So, essentially then we have noted down that these operations are occurring in the physical plane, and this view that we are taking is in the spectral plane, right. So, we need to work out what and how these things are related. You notice that you take the integrated solution and go on to the right hand side and make these operations in sequence, right. You start with A0, then you will have A1, A2, etc., all the way up to A of capital M, and that capital M was defined as the order of the filter. And on the left hand side you have this coefficient alpha, which we call as the filter coefficient, okay. And we actually identified the range of alpha to be between minus half and plus half. Why? Because we wanted to make this A matrix diagonally dominant, so that we do not get into any numerical problem while filtering solution via this equation. However, I will not give you an answer offhand, but I would ask you to show what happens when I choose the alpha equal to half, plus half. You will see that it will not filter anything. That means the transfer function for alpha f equal to half is 1, right. I think it would be a good exercise for you to prove it for any value of m. For m equal to 1, that is what we shown here is the central second order filter, and in your assignment you can actually make use of second order filter. So, do not have to do anything fancy, we can do much more higher order, we can take higher order filters, but we would restrict our attention to a second order filter. Okay. And you can see what does this central mean. The central means that the coefficients on either side, they are symmetric, right, about the diagonal. On the left hand side you have both equal to alpha, on the right hand side you have both A1 by 2. Okay. And what you noticed here, that Taylor series expansion gives you this kind of expression on the left hand side and right hand side, and we demanded that consistency should require that at the basic level uj must be equal to uj hat, and that would mean the coefficient 1 plus 2 alpha must be equal to a0 plus a1. Okay. That was what was required at the basic minimum level, and we called it as the consistency condition. Okay. Now what we could do is we have three unknowns alpha, a0, a1, and we wanted to keep alpha as a kind of a free parameter. We don't wish to a priori fix the value of alpha so that we are left with no control. We want to control the performance of the filter through the choice of at least one parameter, and let that be that alpha. Okay. That means that we need to figure out a0 and a1, and this is one equation that we can use for evaluating those couple of unknowns. The other one, we decided that the transfer function should be equal to 0 at the Nyquist limit. Okay. And how do you do it? Well, we have written down that equation that we see it here. So this is basically that. Please do understand that this is written in the physical plane. This should be a lowercase, although the slide shows they have to be uppercase, but this is what we are doing. So this is your filter so you use the spectral representation of this, and then you can immediately see that this becomes 1 plus 2 alpha. Yeah, so this will give us cosine kh, because this will give e to the power plus I kh, this will give e to the power minus I kh, add it up, you will get 2 cos kh. That we need to do, and we would have u of k e to the power I k x j. That is what we are doing. This should be equal to, on this side we will have a0 plus, if I up again I am going to get a1 cos kh. Okay, and that will be again u of k. So this is dk, and this also would be evaluated at the same node, and this is what we get. And basically this is our u hat and this is u. So you can see if it works for all k, so we can get rid of this, equate the integrand, and this, since they are operating on the same node, so we can get rid of the common part. So this is what we expect, and you can very clearly see the transfer function for this second order filter would be equal to u hat by u, and that is equal to 1 plus 2 alpha cos kh divided by what we have written a0 plus a1 cos kh. Okay. One of the function of these filters is to basically stabilize the computation, and by now I think we all agree that most of the time in numerical computation the problems arise at the highest wave number, right. So that is what we decide some qualitative feature of the transfer function. That is what also we need to keep in mind. So we like to do that, and what we expect this transfer function should be of that nature which will not alter the solution at low k. Okay. So, it should remain flat equal to 1, and what we would like it to do, it should attenuate all the higher kh component, and this is what we expect to happen, that the transfer function should be equal to 0 at kh equal to pi, and that is what we are talking about. So, at kh equal to pi, so this will basically tell you that kh equal to pi should be equal to 1 minus 2 alpha I have done full term. Okay. Okay. So, that is what I was myself getting surprised. So, we would get then the numerator, we get A0 minus A1, and the denominator is 1 minus 2 alpha, and that also tells you why you do not want alpha to be exactly equal to half. What happens if alpha is exactly half? In addition, if I take alpha equal to half and demand the transfer function at kh equal to pi, it becomes indeterminate form, but you can work it out and show that that becomes 1. But that is just what I am telling you for a second order filter. But the thing that I asked you people to look at is that for any order filter, you can show alpha f equal to half will give you transfer function equal to 1. You should be able to do that. But then if I want to do this equal to 0, then of course I require the numerator to be equal to 0. That gives you A0 should be equal to A1, right? And if A0 equal to A1, then look at the previous solution, I mean the equation here. If I put that equal to that, and this is what we get. A0 equal to A1 should be equal to half plus alpha. Okay. So, now you can actually realize that in your assignment what you need to do is basically find out, you know the value of k where your web packet is. Next thing that you would like to do is figure out the value of alpha, where for that value of alpha you should get say suppose this is my kh. I choose some discretization number of points. I have not talked about how many points you should take, right? Maybe you are choosing some point here. You have chosen h in such a way for the web packet that you are here. So, this value you know. So, if I know what this is, let us say this is 0.955, and then if I know this is 1.05, and if I multiply by 0.955, do I get 1? No. Then what I can do is I can keep plotting this transfer function for different values of alpha, right? And that is distinctly possible for any order filter that you do, and this is kind of a result that you are seeing here, that look at the solid line for a moment. We are focusing upon second order filter. Those are given by the solid lines, and these are the two values of the filter transfer function for alpha equal to 0.2 and alpha equal to 0.4. What you notice that for smaller values of alpha, transfer function starts deviating from 1 earlier than what you get to see here. And what did I say, that when you approach alpha equal to 0.5, what did you get? You will get this solid line to go straight up to 1, and at the Nyquist limit it will just fall off to equal to 0. That is your box filter. That is what is one associates with spectral method. We have talked about it, right? The discrete method, we keep on attenuating the solution smoothly, but when we adopt spectral method, then there what we notice that it works like a box filter. So, you do not do any alteration for all possible kh, and once you have up to the grid resolution, that is where it falls off. So, alpha equal to 0.5 would take you along a line which will go straight all the way up to pi, and then it falls to 0. But anyway, you are noticing that your control in solving the problem revolves around two things. One is choosing the value of appropriate alpha, the other thing is h, how many points you can take, but given in your assignment, I have removed the second degree of freedom, because I prescribed the value of kh. So, if you are not given a value of k, you are actually given a value of k. Why did I do that? Because we have noticed that all our numerical properties depend on this non-dimensional k, right? That is the kh. So, that is what we have done. So, all you need to do in your exercise would be to choose appropriate value of alpha, so that the transfer function multiplied by the unstable g of k, this right hand side should give you exact value of what at the wave packet number. Okay. Now, this what we just now talked about is for a second order filter. So, suppose we want to look at higher order filter, what do we do? Well, we keep taking more points on the right hand side, right. For example, if I want to add on an additional set of terms, I could do it like this. I would write it a2 by 2, and then I write u j plus 2 plus u of j minus 2, right. So, what will that do for us? It will do a couple of things for us. Now, keeping alpha still as the filter parameter. So, we are going to choose it freely by on our own accord. That leaves us with the task of evaluating 3 unknown coefficients a0, a1 and a2, right. What will be the consistency condition here? Left hand side will have still the same thing, 1 plus 2 alpha. What do we get here? A0 plus right. Is that okay? So, this is a condition that you must satisfy. So, for this we are talking about a higher order, higher than second order filter. Now, talking about this order business, I suppose you would all realize that order comes from this Taylor series expansion, right. In this exercise, we have just simply have done this. So, the next level of terms which are unbalanced are the second order, that is why I called it a second order filter. In the next level, what we should be doing actually, we would be equating the coefficient of the next set of terms. So, what should I get for the next set of terms? That should be the coefficient of u double prime, right. If I look at that on the left hand side, I will get 2 alpha, right, and on the right hand side, what should I get? A1, right, isn't it? A1 by 2, right, and from A2 I would get what? A2 by 2 into 2 square, right. So, that is what you have to do. So, for the next higher order filter, you would be actually be satisfying this two equation, and then what remains to be done? Forcing the transfer function at the Nyquist limit equal to 0, that will give you the third equation, and then you will be solving for those 3 equations to fix A0, A1, A2 in terms of alpha. In fact, let me give you this reference where all these things are given, all these coefficients as a function of alpha is given. Okay, this paper is by again the same group. They have done most of the initial development. Okay, this is in AIA journal. Okay, you can take a look at this, where this people have really worked out order filters, and just to give you at least one more set. So, will the next order filter would be a fourth order filter. That is what we have been looking at here, this two equation plus the transfer function at pi equal to 0 would give you A0 as 5 by 8 plus 3 alpha by 4. A1 would be equal to half plus alpha, and A2 is minus 1/8 plus alpha by 4, right. So, we have this fourth order filter defined by these three coefficients in terms of alpha, and we have actually also seen the fourth order filter behavior. And you notice that the coupling of the terms on the left hand side and on the right hand side ensures that the order of the filter always increases by 2 by adding one set of extra term on the right hand side, right. That is what we have done here. The moment we have added this A2 term, we have gone from second to fourth order, right, and those are the coefficients that you get. And well, let me just fill you with this information, and I will not give you the rest. You can take a look at the original source material. And then we should have the additional coefficient A3, and that works out to this. Yes, is there any question, any observation, anything that you would like to share? Tell us. No, not related to anything of this kind. Okay, fine. Okay, so if I basically look at this, this is the generic equation that we are talking about in the tridiagonal framework, but we can actually make it even more general by looking at expressions of this kind. As I told you, we write it like A times u hat is equal to B times u. That is the nature. So that actually works out an expression of this kind, and we have written it out in the k plane, right? We have written it out in the k plane, so that you can get this. What is special about this compared to this what we have been looking at? What is the difference? The difference is the previously what we are doing a kind of a local analysis looking at the jth node only, and whereas here what we have done, we have been able to integrate the whole domain together and obtain the transfer function on a node by node basis, right? We can get all the transfer functions for different jth node by an expression of this kind. So whatever we have done, if we can write it down for the full domain, right, we will write it down for the full domain in the following manner. So we will not write it like this. So what we are saying is we are writing this A times uj matrix should be equal to B times this vector uj. Now, as you can see that what we could do is this is an implicit equation. Suppose I am looking at say the jth node, let us call it a different running variable ul. So if I am looking at the jth node, I would be looking at the jth line entry of the A matrix multiplied by all the u hat L's, and that should be equated on the jth line entry on this side. So that basically would give you J1 U1 plus let us say AJ2 U2 etc., and let us say we have total n number of points in the domain. So we will be writing AJN UN. So that is your left hand side, and on the right hand side we will have similarly BGJ1. Now this is U1 and so on and so forth. Now what we did, what we originally did for the analysis of all compact schemes, the same thing we do, right? We can refer everything back to our representation in the k plane. So what we could do is, these are sort of constant coefficients, so they could remain as it is, and this I could write it as say u of k e to the power I k x1 dk. So that is this term, and then I could write E A J2, and this we are writing u hat, and we will write u hat of k e to the power I k x2 dk, and so on and so forth, equal to the same thing. We can do it on this side. Well, you can keep the bj1 outside, and you will get u of k and e to the power I k x1 dk, and so on and so forth. So what I tried to do is we try to use here the same idea of projecting this phase into the jth node phase. So what we would be doing then, just simply write the same thing. We will write u hat of k, and this I will write it as x1 minus I k xj times e to the power I k xj dk. So that is what we are going to talk about. So we have a term of this kind here. Well, and from here also we can write down similar thing, we will write u hat of k e to the power I k x2 minus I k x j and then e to the power I k x j dk. So, we can write all the quantities in terms of the jth node phase, okay. And then of course, you notice this is what you are going to get, right. On the left hand side you will get a j l e to the power I k x l minus x j, and then this is u hat, let us say evaluated at T n, that is what you are going to get, sum it over all possible l's, right. That is what we have done here. The same way you are doing it on the right hand side. So, now since you have obtained this expression for the jth node in mind, so the corresponding ratio of u hat by u should be the transfer function t, if I call it t of k, but now it is specifically done for the jth node, right. So, what happens is you notice that whatever the filter formula that you choose, eventually you will have to write out a complete set of equations. And if you have noticed, for your second order filter, we did write it like this. So, you can see that we can start using this expression from j equal to 2 all the way up to n minus 1. One thing we must also realize that in many of the physical problems, well, in all physical problems, you would require boundary conditions. That means what? At j equal to 1 and j equal to n, conditions would be given to you, either in terms of the functional form or in terms of the derivatives, right. So, you can do that. So, if you look at that, then there is a need for applying this formula from j equal to 2 to n minus 1 only. So, when I am trying to use a second order filter like what we have written out there, we need to apply it from j equal to 2 to n minus 1 only. So, we can clearly write this equation, right, without any problem, because we can use the same stencil for all the interior points. There is not any ambiguity there. However, what happens is, if you want to be a little more ambitious in terms of higher order and would like to go to, let us say, fourth order filter, then what would you do? Well, as we have written, we would be then adding this next pair of terms, right. That would be this a2 by 2, and then we will write u j plus 2, and this will be u j minus 2. Now, you can see that this equation, whether you are doing a second order filter, a fourth or sixth, any order filter, what you do, the left hand side always remains the tridiagonal thing, because we do not want to increase our computational overhead. The left hand side remains the same. It is only the right hand side points, those are used in filtering, keeps increasing with the increasing order of the filter. So, in the fourth order filter, we need to take j plus 2 and j minus 2. But then we have to now think of the following, that we can apply this from j equal to 3 to n minus 2 only. What happens to j equal to 2 and n minus 1? We cannot use this expression. We have to do something more, and doing something more means the left hand side would be just the same. So, all we are looking at basically asking for for j equal to 2, what should we be doing? The left hand side will keep it as it is, because that does not cause any problem. On the right hand side, of course, you have to be concerned about what you could do. One possibility is you revert back to second order filter. So, then you have no problem. So, basically then what we are saying, that we are applying a fourth order filter from 3 to n minus 2 at j equal to 2 and j equal to n minus 1, we are going back to second order filter. And then once again we have no ambiguity. And what is it called, Yogesh? Lowest order compact, is it? People have all kinds of mouth filling names for it. So, this is what is called as least ordered, LOC filter, this is what they call. So, you keep on having always everywhere the central stencil. Why are we so particular about central stencil? I think any one of you would be able to tell me. If I do not have a centered stencil, what other options I can have? I can have a one sided one. If I use a one sided filter, what will happen? You have seen the Taylor series expansion for the second order filter. We had always second derivative, fourth derivative, and so on and so forth. The moment we do a sort of a one sided filter, we are going to get also those odd terms. And what those odd terms would do? Would do, apart from adding dissipation, it can add to first derivative. If it is a first derivative, what do we call this as? That is convection, right? That is our convection equation. We always have seen del u del x is a convection term. But if I have a third derivative, fifth derivative, we call that as dispersion term. So, basically a convection term is a special case of a dispersion term, but in actual parlance we always will call the first derivative as a convection term, and that would do what? Well, you can understand what happened, what we have seen. G of hat was, let us put it as J. Now, we also know how to do it for the full domain analysis, and we could write like this. That would be G of the original numerical method times this. So, if I take central filter, T is real for central filter, right. So, it is real for central filter, whereas this becomes complex for, if I call them as one sided filter, that is what it is. For one sided filter, T of j becomes this. Now, if you recall, for all those error analysis that we have done, we have seen G itself can be complex, and its real and imaginary part fixes the phase shift, and that helped us in finding out that C of n, remember the numerical phase speed. So, suppose you have struggled to get some good combination of kh and nc to get a correct value of gj of k, but somehow it becomes slightly unstable. Then you are trying to use this filter to bring it down to its neutral case. But then if this is becoming complex, it actually puts you in a dilemma, because your original G of j is correct, but now that you are trying to add a complex transfer function, that will shift the phase relationship of G imaginary and G real. So, you know that there would be some sort of a conflict, and it is for that reason that we always try to avoid using one sided filter, and this LOC filters are one way of getting around, okay, getting around. However, we will talk about time permitting that sometimes we may actually intentionally design upwind filters for better properties. So, that if we have time, we will get there. Okay, so what happens is now you can take a look at these figures, and you have in front of you the transfer function for second, fourth and sixth order filters, okay, and they are shown here. Say for a fixed value of alpha, as the order of filter increases, you have lesser filtering at low k, whereas the descent is rather rapid at high k, right. So, the sixth is this hollow circles. So, that is what you are seeing, that it does not alter the original amplification factor, maybe all the way up to 1, but then it starts dropping off, whereas the fourth order filter, this may start happening at 0.6, 0.7, and the second order filter, it may start happening from 0.3 itself, right. So, you can see that is where the order of the filter comes into picture. However, when there is another way of altering the filter property is by increasing the value of alpha, I mean changing the value of alpha, and what you are noticing here, the increase in value to 0.4 actually improves. Well, depends on what you mean by improvement. Here we are talking about improvement in terms of not interfering with the original numerical method. It only should interfere at high k h. So, in that sense, alpha equal to 0.4 would be considered an improvement over alpha equal to 0.2. So, this is what we could do. And now, there are ways of, as I told you, to not adopt central filter, but have upwind filter, and people have suggested, this paper itself suggests a host of them. Unfortunately, though, they did not do the full domain analysis, right. They did not do the full domain analysis, and that is why they have had no clue of what is happening for the filter in the full domain. And because we have the wherewithal to really analyze, and that is what we have done. We have shown you here the transfer function, the real and imaginary part with one sided filter, and you notice that j equal to 1 and n, we do not alter the function, right, because of the boundary condition, we do not want to alter. So, that is why we have just shown here an imaginary line at 1. So, that is what happens. That means at 1 and n, we do not interfere, but at 2 and n plus 1, what happens? We see some kind of a overshoot. So, what happens is your desire is to reduce the amplitude at high k h, but for j equal to 2 and n, you can see there is an intermediate range over which, instead of attenuating the function, this transfer function actually amplifies it, right. Now, another thing that I did not talk about is that this is a post processing operation, right. We are doing numerical calculation. After every time step, we can use a filter. So, option remains with us. We can also not use a filter after every time step. So, the frequency of filtering is also an additional degree of freedom in your armory to actually control the quality of solution. So, what we are noticing, that if we do filtering at every time step, then you would notice that at j equal to 2 and j equal to n minus 1, this filter can actually amplify. So, if your original intention is to make an unstable method stable, you are noticing that at j equal to 2 and j equal to n minus 1, you are not getting that. So, got to remember that, and the imaginary part of course will tell you what is happening. This will actually bring in the first derivative, and this kind of operation attenuation is due to the even derivative, and this kind of values that you are seeing in this lower frame causes instability, right. We do not want them to be there. So, what happens is basically then if we try to use some of this filter boundary filter as suggested in this paper, then we notice that for j equal to 2 and j equal to 3, we actually end up having numerical instability as opposed to what was our initial intention to stabilize the computation. It actually destabilizes near the boundary, whereas of course on the other side you have the complementary phenomena, it actually attenuates much more severely. So, basically I am not going to go much more deeper into it, just to tell you this is that LOC approach, that is what we wrote there, least ordered centered filter operation that one can do. So, basically this is the way that we have plotted this figure, that at j equal to 2 and n plus 1 we have used a second order filter, at j equal to 3 and n minus 2 we use a fourth order filter, and rest of the points we have uniformly used a sixth order filter, and the corresponding centered filter behave like this. Well, this is much better than using one sided filter, right. We do not have to worry about numerical instability. You may lose some bit of accuracy at lower kh near boundary points, but by and large it looks pretty decent. Okay. And of course, you have additional control over alpha equal to 0.2. Okay.